Graph Theory Class 7 Video 4. In this video we're going to prove that this graph right here, the pentagram, is non-planar. So, like I mentioned in the previous video, proving a graph is non-planar is extremely difficult. So the actual proof in this video is going to be non-examinable. Okay? So the proof of this in this video is going to be non-examinable. All that you need to know for the exam is the fact that this graph is non-planar. You don't need to memorize this proof for the exam, but I'm going to include it in case anyone's interested. So to prove this is non-planar, it's like a two-step process, and the first thing I need to do is prove this auxiliary result, which is if G is a simple planar graph, then I have this inequality. E is greater than or equal to 3/2 times f. So it gives you a bound on how the edges and the faces relate to each other. So let's try and prove this first, and then we'll use this to prove that the pentagram is non-planar. So I need some notation. So I have my simple planar graph, okay, and I'm going to let the faces be denoted by R1, R2, R3, RF. So these are the faces of G, okay? And I'm going to define this function. Let edge Ri be the number of edges touching the face Ri. Be the number of edges touching the face Ri. So for example, if I just quickly draw a graph, and if this is R1, R2, R3, then edge R1 is equal to 3, because there are 3 edges touching R1. Edge R2 is equal to 4, and edge R3 is equal to 1, 2, 3, 4, 5, because there are 5 edges touching R3. Okay? So the thing to note now is that for any face, we always have greater than or equal to 3 edges touching it, because it's a simple graph. So that means the smallest possible face still has 3 edges touching it. So if I add all these things up, edge R1 plus ... plus edge RF, this is greater than or equal to 3 plus ... plus 3. And how many things are there in my ... Well, there's f of them. So this is 3f. Okay? So if I add up edge R1 plus edge R2 plus edge ... whatever, all the way up to edge RF, whatever number that is, it's going to be greater than or equal to 3f. Okay? Now we know a different thing, and that's every edge touches at most 2 faces. Every edge touches at most 2 faces, and this is not too surprising, right? Like, there's edges sort of have 2 sides, so every edge touches at most 2 faces. Okay, so that means that this sum right here, it counts every edge at most twice. Okay, so the number of edges touching R1 plus the number of edges touching R2, so on and so forth. This, adding them all up, counts every edge at most twice. So another way of saying this is 2e, twice the number of edges, is greater than or equal to edge R1 plus ... plus edge RF. Okay, and now all we do is we put these two things together. So we have this one here and this one here, and notice that they have the same term. This term here is the same as this term here. So I can just sort of put these things together and get 2e is greater than or equal to 3f. Or another way of saying that is e is greater than or equal to 3 over 2f, which is what we wanted to show. Okay, so that's that proof done. So we've proven that for a simple planar graph, e is greater than or equal to 3 over 2f. So now we can prove that the pentagram is non-planar. So theorem, this graph right here is non-planar. And it's actually not going to be too bad now that we can use the theorem above. So if it was planar, then we must have that e is greater than or equal to 3 over 2f by the above theorem, right? If it was planar, this would have to be true, okay? And if it was planar, we also have that v minus e plus f is equal to 2, because this is true for every planar graph, okay? So we can rearrange this equation to solve for f. Okay, I don't know, I'm assuming it's planar, okay? I don't actually know a way of drawing it without edge crossings, and I'm just going to assume it is planar, and then I'm going to work out what would f be if it was planar. So we know that just by counting, v is equal to 5 and e is equal to 10. So 5 minus 10 plus f equals 2. Okay, so this means that f is equal to 7. Okay, and e is equal to 10. But the trouble is, we need to satisfy this equation up here, and 10 is not actually greater than or equal to 3 over 2 times 7, because 3 over 2 times 7 is equal to 10.5. So this is a contradiction. Okay, we assumed that the graph was planar, and if it is planar, it has to satisfy this equation right here, but we just saw that it doesn't satisfy that equation, so therefore the graph isn't planar. Okay, it's an abstract proof. It's what you call a proof by contradiction. Okay, that's the end of this proof, showing that the pentagram is non-planar. Like I said at the beginning, the proof of this fact won't be examined. It's sufficient that you just know that the theorem without the proof. But this is how you go about showing graphs are non-planar. It's not an easy thing to do. Okay, that's the end of this video.